Like in the atoms, the overall electronic orbital in a molecule can be approximated by the orbitals of individual electrons. The one-electron orbitals of molecules are called molecular orbitals. The electrons occupy molecular orbitals in molecules, just like they occupy atomic orbitals in atoms. The distribution of electrons in the molecular orbitals is the molecule's electron configuration. The principles of electron configuration in ground-state molecules are like those in the atoms, that is, Aufbau principle, Pauli exclusion principle and Hund's rules. A qualitative descriptive tool explaining the electron's configurations in molecular orbitals is molecular orbital diagram. Molecular orbital diagrams are diagrams of molecular orbitals, shown as short horizontal lines in the center, flanked by constituent atomic orbitals for comparison, with the energy levels increasing from the bottom to the top. Lines, often dashed diagonal lines, connect molecular orbitals with their constituent atomic orbitals. Atomic orbitals and molecular orbitals are filled with electrons according to the principles, symbolized by small vertical arrows whose directions indicate the electron spins. For example, in the ground-state hydrogen atom, the 1s orbital is occupied by one electron. In the ground-state hydrogen molecule, these electrons occupy the same 1s bonding orbital for its lowest energy and have opposite spins. In the molecular orbital diagram of the dihelium aggregate, each helium atom has 2 electrons in its 1s orbital. There are totally 4 electrons in the molecular orbitals. They occupy both the 1s bonding orbital and the 1s antibonding orbital. The total energy in the dihelium aggregate is higher than that of 2 helium atoms. Thus, dihelium is not stable and cannot be considered as a molecule. The molecular orbital diagram for dioxygen requires the introduction of the overlap of 2s and 2p orbitals. The 2p orbitals are degenerate and oriented mutually perpendicularly. The 2pz orbitals can overlap end on, forming a bonding sigma orbital and an antibonding sigma orbital. They are non-degenerate. The 2px and 2py orbitals can overlap side-on. The resulting orbitals are pi orbitals. The bonding pi2p orbitals are doubly degenerate. They are shown side by side. The antibonding pi2p orbitals are doubly degenerate as well. Due to larger overlap between 2pz orbitals, the energy difference between bonding and antibonding sigma 2p orbitals is greater than that between bonding and antibonding pi2p orbitals. Pay attention to the fact that the antibonding pi2p orbitals are each occupied singly with electrons of parallel spin due to Hund's rule. In diboron, the atoms are close enough for their 2s and 2p orbitals to interact, which can lead to a change in the expected order of molecular orbital energies, a phenomenon called sp mixing. As a result, the sigma 2s orbitals are lowered in energy, whilst the sigma 2pz orbitals are raised. For the diboron, this results in the bonding sigma 2pz being higher in energy than the bonding pi2p orbitals, which is where sp mixing is most evident. Pay attention to the fact that the bonding pi2p orbitals are each occupied singly with electrons of parallel spin due to Hund's rule. Bond order is a measure of the multiplicity of a covalent bond between 2 atoms. It is defined as the difference between the numbers of electron pairs in bonding and antibonding molecular orbitals. The bonds with order 1, 2, and 3 are single bond, double bond, and triple bond, respectively. To calculate the bond order, only the valence electrons need consideration, since the core electrons occupy bonding and antibonding orbitals equally. Here, homonuclear diatomic molecules in period 2 are used as examples. Their bond orders can be easily calculated from their molecular orbital diagrams. Bond order gives a rough indication of the stability of a bond. Generally, the higher the bond order, the stronger the bond, in other words, smaller equilibrium distance and higher dissociation energy. Thus, dinitrogen with a bond order of 3 is the most stable in this group. The aggregate with bond order 0 is unstable, such as diberyllium and dineon. A non-bonding orbital is an atomic orbital which does not overlap with other orbitals. For example, in hydrogen fluoride, a sigma bonding orbital and a sigma anti-bonding orbital are created with the 1s orbital of hydrogen and the 2pz orbital of fluorine. However, 2px and 2py orbitals from the fluorine do not have any other orbitals to combine with due to their wrong symmetries and become nonbonding orbitals. A nonbonding orbital is the same in the molecule as in the atom. Electrons in nonbonding orbitals neither increase nor decrease the bond order or energy between the involved atoms. For example, the 2px and 2py orbitals from the fluorine atom are occupied nonbonding orbitals in the ground state of hydrogen fluoride molecule. The electrons occupying them have the same energy as in atoms and do not change the energy or the order of the hydrogen-fluorine bond. Molecular orbital diagrams can be used to deduce magnetic properties of molecules. Paramagnetism is a form of magnetism whereby a substance forms internal induced magnetic moment in the direction of an externally applied magnetic field. Paramagnetism is due to the presence of unpaired electrons in the substance, whose spins have magnetic moments and act like tiny magnets. An external magnetic field causes the unpaired electron's spins to be parallelly aligned to the field, so that the paramagnetic substance is weakly attracted by applied magnetic field. Molecular oxygen is a good example of paramagnetism. It has unpaired electrons in its antibonding pi2p orbitals. When liquid oxygen is poured into the gap between the poles of a pair of strong magnets, the liquid is contained in the gap owing to its paramagnetism. Diamagnetism is a form of magnetism whereby a substance forms internal induced magnetic moment in the opposite direction of an externally applied magnetic field, so the substance is weakly repulsed by applied magnetic field. The electrons in the substance generally move in orbitals like current loops. Any applied magnetic field would generate currents in these loops that would oppose the change. These currents induce magnetic moments in the opposite direction of the applied field. If the substance has unpaired electrons, these magnetic moments are overcome by the spins. Therefore, only if all electrons in the substance are paired, the substance is diamagnetic. Molecular water is a good example of diamagnetism. It has all its electrons paired in the molecular orbitals. At the Nijmegen High Field Magnet Laboratory, a live frog is levitated inside a vertical bore in a magnetic field of about 16 teslas, due to the water in its body repulsed by the super-strong electric magnet beneath it. Larger molecules such as benzene can form various molecular orbitals with different symmetries.